We're going to talk about residual network, or ResNet. Res stands for residual. If you don't know already, residual network paper by Kaiming He, who is currently a professor at MIT, is the most cited papers in deep learning ever. And it's one of my favorite papers. So we're going to talk about why this paper is such a big deal and introduce this concept that skip connection and the shortcuts for gradients that open the door for really deep learning with hundreds of layers. It turns out to be a solution to the problem with exploding and vanishing gradients. Let's look at first order logic. I prepared the example that with a bunch of living organism in animal kingdom, also plant kingdom. So a lion, dog, cow, pig, shark, croc, bee, and a tree. And now let's start with only two features as input. So I eat meat. So lion, dog, eat meat. So the 1, 1 over here. Shark and crocodile, they also eat meat, 1, 1 here. But bee, tree, cow, pig, they don't. A mammal, so who are the mammal? Lion, dog, cow, maybe use this one. Lion, dog, cow, pig, and shark. No, shark's not a mammal. So the first four are mammals. So 1, 1, 1, 1, 0, 0, 0, 0. Okay. So now I have a first layer of linear layer, and these are the weights and biases I have. Can we interpret what this neuron might be doing? If you see 1, 1 minus 1, what do you think the neuron is trying to do? So one interpretation is that it might be thinking, let me just use the red color. Since 1 and 1 is means like positive, it kind of looks like an AND gate to us. So for first neuron over here, it's right over here, A1. This is my new feature after activation. The first neuron seems to be doing is meat, okay? Meat and mammal, okay? And how about second neuron? Second neuron, what does it mean? What kind of meaning is trying to capture? It's 1 minus 1. So it means it's going to meet and not mammal. That's one. That's a way that we could potentially interpret this. How about A3? The third one is minus 1, 1. It means it's opposite of this. It's not meat, doesn't eat meat, and is a mammal. And lastly, is both are negative. So it's going to be doesn't eat meat, something that doesn't eat meat, and also not a mammal. So in this example, I purposely fill out the entire truth table of possibility with 4 different values. And then this is going to be just a linear operation. And then have Residual over here. Okay, and just to check the result, you can inspect the equation. You can see this is the multiple maximum location and some Residual. Okay, and then just check whether I get the result I want. So last one, what would be among this? Who is not doesn't eat meat but also not mammal? So I think it's B, and B doesn't eat meat, also not a mammal. So since but shark and crocodile are, and bee and tree are not me. So I expect bee and tree, and which match the intuition over here. And how about just pick another one to check? Who is eating meat but not mammal? Who is eating meat but not mammal, which is our A2. Okay. There'll be shark and crocodile, right? So shark and crocodile is over here, A2. So this is meat eater, not mammal. Mammal, not eat meat are carnivores that are not mammals, the shark and crocodile. This will be not meat eater, but also not a mammal. It's B and tree. Okay, so it makes sense that first order logic being captured by this linear layer. Okay, and then we can look at another example. This example is I use another example, but I'm gonna have a bit more input. These are the 3 different input. Just me and mammal. I now have a third one, fly. Who flies? Looking down the list, bee is the only thing that's fly. Okay, so I just add another features. And then now we look at the layer, first linear layer. Now you can understand that first linear layer, what it does is that it's going to take these 3 features, trying to mix them using an AND operation or some other combination. And operation is easier for us to explain, so we'll just focus on that today. All right, 3 inputs. How many different possibilities you can write up the logical operation involving AND 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 so it's going to be 2 to the third power at 8 different operation. But for my layer, in the linear layer, I only have 4 neurons. So 4 neurons, they were trying to find the 4 out of 8. They could not possibly learn all the possible combination, but they could potentially pick 4. So this is what, as a result, this is my interpretation. For first one, what is the first one? First one going to be just take the first feature, which is meat. And second one is going to be not meat and not mammal. Okay, so let's move over here, more space. Third is not meat and fly. So who is not the meat eater, but fly is going to be, I think, right? So it's just moving down the list is here. Okay, so it's actually picking up B. That's correct. And the last one, what is the last one? It's going to be not a mammal and don't fly. Who will be not a mammal that doesn't fly? There are quite a few of them, right? So shark is doesn't fly, croc doesn't fly, and tree doesn't fly. So that it does map these 3 ones over here for my last feature. So we apply first order logic to this example involving 3 features as input, and then I'll have 4 neurons over here that picked up 4 different concepts based on those 3. There are 8 possible ways to mix them, but in this case, we only pick 4. Neurons only pick the 4 most prominent with respect to the objective function. Let's look at the second order logic. When we have more than just one layer, we could put first layer, first order logic and just mix them together and it becomes second order logic. What does it mean? So, okay, so now I have these 2 layers, 2 set of weights, and then let's interpret what is happening here. So eventually we have this A1, A2, A3, A4. This is our second order features, all right? And so, so these are correspond to here and here and here and here. This way gonna tell us something. Let me just look at the first one. The first one, we have this and this. They are non-zero. Let's erase this. How can we interpret this? So this is going to be actually coming from here. Okay, so that is A2, A3, but this A2, A3 are different from here because I didn't index this. Let me just put this prime so I can differentiate them. These are, and this is A2, A3 without prime. Okay, and so now with this, I know that earlier on, I see this is going to be sort of like an AND gate operation. So I have no A2 and not A3. Okay, so that's what this second layer, second order logic is supposed to possibly capture with this. And so now I'm trying to reason what is A2 and A3? What can I interpret A2 and A3? We're gonna go back up here. So these are the 2 things, 2 rows. And weights, how can we interpret this weight? So these are A2 and A3. But this one going to correspond to F1 here, F1, F2, F3, F4. These are the first input features. And so for, let's look at A2. So A2 is going to, seems like F1, involving F1, F2. So F1, F2 are meat and mammal, and they are negative. So my A2 is going to be F1, F2, right? What is it? F1, F2 is not meat and not mammal. That is my A2 coming from here. And my whereas my A3 is going to be, what is A3? A3 is not meat. And the third one is fly, okay? And fly, okay? So when put it all together, and there's another not here, so maybe just put another parenthesis here. And this comes from here. So this is my interpretation. You put it all together, and they'll be kind of like not meat and not mammal. Let's see here. Not me and not mammal and not of the not, me, and fly. It's very difficult for us to just say that. So I'm trying to write down the English sentence. Is probably is one way to describe this. A non-meat eating non-mammal that cannot be a non-meat eating thing that flies. That's what this particular neuron is trying to learn. The particular concept, a second order concept or logic. All right. Hopefully that you start to see that the takeaway is that every time you have a layer that will basically combine the logic from the previous layer. If the previous layer is a fourth order logic, and this layer will go to be second order logic, you can see the extension of this. If you have another layer, it's going to be third order logic, higher order logic that based on the previous layer and so on. All right. So in the next section, what I'd like to talk about is that what if we would like to be able to mix the first and second order logic together? So in the previous case, when we consider the second layer, each weight is only weighting the logic from the previous layer. Okay, so in this case, I have A1, A2, A3 here that coming from this layer. But what if, in this case, I like to say that, so A, if I remember this one, A3 is not me and fly. Okay, write it down. Not me and fly, or just say, what is it? Not A3. This is not A3. Sorry, not A, sorry. It's A3 here. This is A3. If you look at the red part. But what if I like to add F into it? F actually come from the input. It's like a two layer, I mean, a two layers above here. So F1, I want to get F1 over here, down here, and then with this one. So the trick is to add another identity matrix over here, and then allow us to combine the A's. A's are the first order logic, and F are the input features. So we'll be able to access the input feature even in my second layer over here. So we'll be able to have something like danger. Not actually, no. It's the first one is what's it? Meat. And A3, what's A3? And meat. And this doesn't make sense. Okay, but and not meat and fly. So they'll combine this together to get this logic. But it turns out me and not me just doesn't make sense. That's why A1 at the end, oh, 0. So this is not a great example. But let's just consider the last row. We have this thing, the new feature called danger. Danger is my fourth feature. But then if you look coming back up here, somehow in the second layer, all the weights to danger are 0. And if we don't do anything special, we have no access anymore in the second layer and to the concept of danger. But what if the concept of danger is quite important in our second layer? We already lost access to it. It's very hard for the network to recover from that. And so what is will be dangerous? You look at shark and crocodile and bee, that's kind of dangerous. Maybe it's important to understand here. So I want to say, what is danger? And this thing. Danger, but they don't eat meat and they also fly. What is this dangerous organism that doesn't eat meat, but it flies around here? So if you are thinking about some buzzing sound, yeah, this bee. Bee will be something that dangerous, doesn't eat meat, and they can fly. If you get too close, you might get stung. So this is like this one, okay? So let's just, I would like to do another just trace again. So I have this, I'm going to use green to denote that this is my second order feature. And this second order feature is composed of this number 3, right? So I can go to number 3 here. So number 3 is here, this 2. This is too thick. Let's just do a thinner here. So this 2. This 2. This 2. Let's just kind of like it here. Okay, do this way. Okay. This 2 first order logic give us this second order logic over here. Okay. And then this, I use another color and to show that this is my input coming from here directly. So this is give me the first order logic. So if you can put it all these two together, you can visualize that By having extra identity matrix here, they allow me to compose this linear combination based on features from two different layers, so mixing across orders. So we have a lot more flexibility that we could take something from the first order, take something from the first input, and to combine new features. So we're not just restricted to the feature from previous layer. Okay, and then this becomes really powerful. Turns out for the network to capture this higher order logic without losing access to more like global knowledge further above the layer. Okay, so you can see that eat meat is a kind of bigger global concept. As you go down there, it becomes more specific. Not eating meat and not flying, as you can see. But sometimes you want to go back to the global concept become important again. And if you don't have this mechanism, it's very hard for the network to access the global larger concept about the layer in the shallow part of the network. As you go deep, so next section, I'm going to talk about skip combination. So the skip combination refers to this technique to allow us to bring the logic from the previous layer in your stack so you can access it. It makes you're not limited to rigid layer to layer boundary when you're trying to pull logic together. This is a very famous diagram in the residual network paper that you have two layers, you have this little matrix here, down here, and you can add to your feature. So I have this schematic based on our natural representation to break it down so you can see more details what's happening with this diagram. So the goal is to be able to have this skip connection down here. So earlier example, I justify why this skip connection is important and be able to mix in logics across different layers. Let's review this. I have two linear layer within this form before. And first layer, we have linear layer and we have activation function, linear layer, activation function. And then in the second layer, we have a linear layer. But before applying activation function, which is not clear in this diagram, the diagram doesn't tell you that where's Residual. So we have Residual here, but also have Residual here, but after this addition. So let's look at how this addition work. Suppose this is fx, the output from this linear layer. Then we'll get the h of x. I like this to be this output from linear layer, but we bring the input earlier on from here. So that's what this arrow means, okay? And then once we have that, and then we take the residual for both together and to get this. So this is the residual of this fx plus x, okay? And so what I want to do is that let's just do, just delete this and try to re-implement this. So this is going to be, before I will just pass through to Relu, but now before I pass to Relu, I'm going to take this is fx, and then plus, where can I grab this? I'm gonna go all the way up just so you can see that when I actually allow this input to pass through two layers and to be added there. So this is a skip connection. Now, this is an addition of the linear layer output over here, which is this green thing, and then also the feature or logic from earlier on, which is the yellow thing, and you get this one. Then once you have this one, then you will take the residual I should implement residual here and to take the result of combining the two terms. Okay, and then this is a new residual function. So that is the operation behind this particular diagram. So x plus fh, and this is the skip connection. Let's call it this right here. So this is so-called skip connection. Skip a couple layers in order to contribute the concept or logic or the feature to the decision that's made over here. You might wonder, why do we use the word residual? Where does the word residual come from? And so this is the exercise that's trying to explain what residual really means. So to the left is the skip connection, which I looked at. And to the right, I also put together a network, two-layer network, but more like a normal two-layer network without skip connection. And the one thing you want to pay attention to this network is that it has the same output. I purposely manipulated so they have the same output over here. So both are trying to learn this function hx. this is the goal. And then you can actually visually verify that for blue, the blue numbers are exactly the same, but weights are slightly different. But in the skip condition case, in order to get this number, so these are the addition of the two, fx plus x, okay? So if you would manipulate this method a little bit, so here, if I have h of x equals fx, f of x plus x. So if we move the term around, what is f of x, f of x? So f of x is over here. What is this thing? What is the green thing? The green thing is going to be the blue, which is h of x, minus the input. So did you see this term? So basically just move the x term to the left. And so f of x equals h of x minus x. And so if I want to prove this using these actual numbers, then what I will do is I will just grab my f of x. What's my f of x? F of x is from the residual example. So that is the network. So okay, actually no. Why is it spelled? Let's fix this again. So this one, make sure I delete everything inside, and then I'm gonna copy this thing. So this is my f of x. You can see the value. I want to understand what f of x is. So f of x is my h of x, which is output, minus x. My x is going to go up here to grab this. So this is my x. Okay, so once we have that, just to make sure it's actually the same. Are they the same? No. This minus this should be this, but this is I just copy. I cheated. Let's redo again. So this thing is going to be this blue thing, minus x. Okay, and it turns out these are the same value of this green thing. I managed to match the value in the green area. So because of that, when this h is for output, but x is actually input. So what fx really means is to model what additional information you have to add to the x. So in order to become hx, so how can we go from x to hx? So, and this is so-called residual. What more do you have to add? Or this is another way to think of individuals over here. How much do you have to take away from the output in order to get the fx? Okay, I know it's a bit difficult to wrap your mind around, but in practice, the way that I like to explain is that in the residual network, in this case, so I'm shift my focus about how I can transform x to my output, h of x, which is a blue thing, and with activation. Instead of thinking in terms of that transformation, through this linear combination or match multiplication and so on, I try to think in terms of addition. What can I add to x? What can I add to x in order to get my output? So I shift my thinking from transformation to just incremental addition, changes, or residual. So I'm learning from the residual. When you hear the word, the network is learning from residual. Another way to think of it is that the network is learning what additional things you have to add incrementally to your input in order to get to your desired output. So in this case, this thing is this green thing. This green thing is what to add. What to add. What to add. And when you have that, and this network is learning about what to add to your x. And remember early on when this form was identity matrix. Then this identity matrix map to this our input. What to add in order to get my output. And this layer becomes that it's going to focus on what kind of features are important to extract from my input. What kind of feature important? And then this going to give me these features. And then you have this way to pull these features in this way and to add to your identity matrix that to your input. Let me just try one more time. In the way that you can understand residual network is that it creates a situation, your first layer, you could be specialized in extracting features by combining the input. And second layer, they can just focus on what feature to add to your input. Whereas on the right-hand side, it doesn't quite have the division of labor. You just keep trying to transform again, and transform again. Hopefully, you get to your output. All right. So I will just end with a more high-level intuition behind the difference between residual case and just regular case. Imagine you are trying to improve your house, that you live in a house, you like to improve it. Each year, you like to make your house better. And the regular transformation is like every time I'm trying to say I want to add a kitchen to my house, I will take all my houses apart, everything, all the pieces apart, and trying to put them together. So that's what this transformation matrix does. And you take everything apart again and put them together. Hopefully, second transformation gives you the kitchen you want. But it's a bit harder for that to happen. And from the residual case, it's more about I'm not taking my features apart. I'm gonna keep my house. But each time I'm trying to just figure out what to add to this house. I want to add the kitchen to it. I want to add a new toilet and so on. Add the new oven, add the new appliance. So there's be more of that procedure of become more addition, adding residual to it all the time. Okay, so hopefully this is my best effort to explain the underlying logic of why the skip connection give you the effect of turning a transformation process into a learning of residuals to add to your features. Once you have this skip connection, you can go really, really deep while avoiding some of the issues we're going to talk about, such as exploding and vanishing gradient. I like to focus on this part, trying to reproduce the original paper. This block layer is actually a convolutional layer, but the concept of skip connection hold as well. Now I want to see that what does this condition really mean? So we have seen this condition over here. So examine it a little bit. In this case, I'm trying to simplify a little bit by not having explicit blue box. I just let it jump to right away. So we can see the equation is going to be, there's a plus sign over here. So here I'm adding this and also this together with this addition operation and then take a residual over here. Okay. And let's just do another one. And another one is that I would like to allow this to skip, not here. Okay. Also not here. It's actually over here right before residual. So we're going to erase this. So this skip condition is actually go from here to here. So this is for the process. And this is going to pass through over here for these blocks. And so if I route redo for this internal step, so it's going to be redo of this part, just regular redo. But here is where things are different. So this redo activation function is going to take this, the feature from previous layer, and then now go back up the couple layers over here to take this one. Okay, and then close parenthesis. So this redo is combining two redo reply activation of the result of combination of two states. Just write the equation, remind you, this is the equation here. You trying to apply redo to here. And then skip one more time. Now I know that the key is that typically we skip right before activation function, but it could just put it be afterward as well. But almost everywhere you put that before activation function, so that help you practice that. And then we're gonna pass through here with plus over here, and quickly just repeat what I just did. So this is going to be the regular redo with imp feature from previous layer. And then we have this new redo, still redo, but just going to take the combination of, this is residual. Now get the terminology right. So this is my residual, add residual to the input from feature from earlier layer. Okay, so I continue to add them. All right, so this is just practice 2 times to show you the pattern of adding seed connection. So next, I would like to talk about projection shortcut. What does it mean? So a lot of times the dimension between layer change. So in the earlier example, we only have 4 dimensions across the network, but a lot of times we would like to go down. For instance, this can we downsample our the data into a smaller number of dimensions. In this case, if I do a skip connection here, then I'm trying to do something similar I'm trying to add this to this, is that the shape no longer match. Actually, I cannot do this. There's a shape mismatch here. So in order for skip connection to work, we need to somehow turn this thing into a same shape in order for this to work, okay? So how does it work? Let's look at the example down here. So we'll introduce this projection shortcut. So instead of feeding all the way down directly, I'm gonna let it pass here and pass over here before I add it. And hopefully this shape now it looks exactly the same as this f. So this is fx, and this is going to be some sort of a transformation of x, say gx. And if they are the shape the same, I can add them. And how do I go from this to this? And it's simply a linear projection that look like going to be, because 4 are going to have, come on, 1, 1, 1, 0. I just randomly create some linear weights over here. If I like to have bias, I can as well. So this is just to draw this. So this is my weight, this is my bias, and then I will be able to use metric multiplication, take this weight and bias, and then go up to select my input, x and the extra 1, rows of 1, and then close parenthesis. Now I have this new projected down format that has the same shape. Now I'll be able to come back down here and to do my ReLU on the combination of the two, my residual again, plus my feature, but the projected version, down projected version of my input X, and I'll be able to combine them together over here and to complete my implementation of skip connection, but through down projection. Okay, so this down projection. So if I move out a little bit to show you in this graphic, so you can see there's some down projection happening here. So they use different color. Let's just erase this a little bit. They use different color to represent region or blocks of residual blocks that have different dimensions. So between blocks, they have a down projection connection. Between these blocks of different dimension, this one is going to be down projection, okay? And everything else is just regular skip connection. All right. The reason why residual network makes such a huge impact is now it's kind of everywhere. Then that you can see this is a diagram for transformer model that was in 2017. Even today, if you see any new architecture diagram, I can count on you have this thing called add and norm. And last week we look at norm, normalization, and add is refers to this adding residual, the concept of adding residual to my features from previous layer. And in transformer architecture diagram, the data kind of flow this way. But for this example that I have here, kind of going opposite from top down. So turn your head around a little bit. But what I want to go through here is that if we put add and norm together, what does it look like? So it turns out a way to look at this two layer we already saw a few times, that correspond to the feed-forward network part. So when we get to the transformer lecture later on, we'll see what it is. But in fact, it's this two-layer MLP, multi-layer perceptron, two different layers. And then we'll fit to this add and norm. So now we look at the add and norm. So let's do the add first. Maybe I'll zoom in now. So add is going to be, in this case, I'm not hiding it anymore. Just like I want to see the result of adding fx plus x. So fx is here, residual. Now we assuming this is residual. The network before learns residual because we're forcing it to learn residual with skip connection. So this might residual f of x and plus x. Okay, now I can implement this. select my fx residual, and plus x is my input from earlier. Okay, here. Okay, so this is now implement the add part. It's pretty easy, right? So transformer, I just implemented the add part of the transformer architecture. And this is the norm. Then we look at norm, and you look this shape. This is going to be a layer norm, which is typical for a transformer with large amount of batch size. So for first, I want to compute mean. So if I do a mean comparison, it's not gonna be accurate because I'm gonna go only get one number. In fact, I want one number per column, so I will use my by column. It's a review of that, but I think it's worthwhile. Worth the time to review this. I want to by column and take my this and then average. So I apply average to each column to get this mean. And then repeat the same thing by column, but this time for standard deviation. Standard deviation here. Okay. Okay. And now I have mean and standard deviation. So I'll be able to take means of and over standard deviation. Okay. So that will be take this thing, this minus my mean. Okay. But now I want to divide this by standard deviation per column. So there will be the centering part of the layer norm algorithm. So centering. So center. Now, and then we also scale. So we have two sets of trainable parameter to decide for each feature. Well, four of them, four features. Each feature, do we need to scale it and shift them? So we'll scale and shift them. So we'll scale each one by multiplying with gamma. Gamma's and add the beta. Beta is the shifting factor. And so this is the result of the layer norm. And I have radius. I already implemented. So this radius. Okay. All right. So what just happened? What just happened? What happened is that I quickly implemented this add and norm part. And also I show you, it turns out this is a very simple feed-forward network. And we're building our pathway to understand transformer later. So I've been referring to exploding and vanishing gradients as an issue that with deep network and residual network happen to solve the problem. So that's important to understand why we are getting exploding and vanishing gradients. Okay, so we have seen this a couple times already, but now we're going to just trace this back propagation path again. So first we're trying to with this loss gradient, and there's a lot of loss function designed to give you this beautiful equation for prediction minus target as a way you can kick off your gradient. And it will go to this one, and when we multiply with this Jacobian of this weights, and we get this, and kind of keep just back propagation. I just like to keep drawing these edges going up many different layers. Okay, as a practice. Every time I draw a stroke, just count the number of strokes I'm drawing. Every time I count the number of strokes I drawing, and so every time this is actually a multiply. All right, and every multiplication involves this weights over here. Okay, it's all this weight is being multiplied with the loss gradient that flow to this area. So if you had lots of multiplication in the chain, if W happen to be kind of big, okay, what do you get? You're gonna explode them exponentially when you have 100 layers. Even if W on average is at 1.5, it could get really big. Similarly, if W on average is like very small and you're going to vanish after you multiply it many times. So to overcome this, if there's a way we could turn multiplication into addition, if you add things 128, it doesn't grow exponentially or doesn't vanish exponentially, right? So this is the idea of having the skip connection. Now let's look at this section. gradient shortcut. So once we have the skip condition, what happened? We have the skip condition down here, and this path allow this gradient to flow back following a similar path over here. Now, when we compute the local gradient over here, you get to add with the gradient over here. So they're just going to use circle to visualize this. Gas can flow over here, and then this is being computed through another path. But they look the same, but they are indexed differently. I just didn't write the index, so I or J there. But I want to give idea, then eventually become plus. So this follow this shortcut paths get added into the gradients. So that's how the math work out. But if we look at another layer, similar idea, we have skip condition go down, and then when we run back propagation, and this gradient we are able to flow back up here and being added using addition. And then here, one more time, you kind of going back up and add it. Okay. So if you look at more from zoom out a little bit, let's zoom out a little bit to 50, and you will see that all this yellow in the previous example, all the yellow are multiplied, but now I have this gradient shortcut now, we have addition. So the gradient can follow this addition path. This also then in the reversal of the residual addition. It turns out it's able to mitigate the exploding gradient and vanishing gradient problem. And add that's the add part of add and norm. And norm part is to deal with that maybe we can somehow normalize this, and so that our weight is not super big or super small, kind of even out. So we wouldn't have weight always bigger, because if all those weights are big, if you that's another source of the problem with the exploding gradients. So add a norm that when put together, going back here, I think that's the one way to explain the solution is that you use norm to deal with this so that your weight wouldn't be like too big and too small all the time. And then you have residual network the add part to allow you to add to turn multiply into addition. That is another way to mitigate the issue. Okay. All right. I spent a lot of time preparing this lecture because it's very hard to explain residual network, even though it's my favorite paper. It's like hard to get people excited. Residual doesn't sound too cool, but when you actually understand the significance, it is the most cited paper in deep learning research for a reason.